Um, I think we're finally in a position that we have enough facts gathered up from previous videos uh, to characterize systems of linear algebraic equations. And by characterize, I mean how many solutions are you going to get and how many free variables. Um, Things we can find out without actually solving the system. We can at least characterize what the solution is, if it exists, and what it might look like. The number of solutions, exactly one, an infinite number, or no solution. I already said if the rank of the augmented matrix is not equal to the rank of A itself, the system is inconsistent. It has no solution. We talked about that in a previous video. If it's not inconsistent, we knew how many free variables there were. It's n, the number of columns of A, minus the rank of A. So we know how many free variables we're going to get. If there are any free variables, even just one, then the system has an infinite number of solutions. If the rank of the augmented matrix equals the rank of A, it'll be consistent, but if it's less than n, the system's going to have an infinite number of solutions. These are some facts we already knew. Here's some cases where it is a consistent system, the rank of the augmented matrix equals the rank of A. I guess you got three different cases. If m is less than n, like in this case here, all these guys over here are going to be free variables. They're going to be non-pivot columns. You'll have, here are the pivot columns, here are the non-pivot columns. You'll have an infinite number of solutions. If the rank, or if m is greater than n, and A is full rank, meaning its rank equals n, what that means, like in this case here, you have more equations than unknowns, but m minus n of them are redundant. You didn't really need them. And the system still has exactly one solution with just the non-redundant equations. If you had a non-zero down here, it would be an inconsistent system. But that the rank of the augmented matrix would not equal the rank of the left side of the unaugmented matrix. And if m equals n, you have a square matrix A, then you have exactly one solution also. And look at, the left side, the A side, after all your row operations, is the identity matrix, which leads me to the next chart. If that is the case, A is squared and it reduces to that identity. We found out before that tells you that this E is the inverse of A. A has an inverse, and its inverse is this E, which is the matrix that summarizes all the row operations. And we also have already proved that if A does have an inverse, then A is full rank. So now we have both way implications. If square matrix it's invertible if and only if its rank is n, meaning it's full rank. It has no free variables, full rank. It also means all its rows and all its columns are linearly independent. And if that's the case, you get exactly one solution, meaning the solution to AX equals B, the X that solves it is unique. We can put it all together, or at least I like to. Here's a decision table to characterize systems of equations. I have two questions to answer. Is the rank of the augmented matrix equal to the rank of the A itself? And is that rank equal to n? The number of columns of A are the number of variables. You can have a yes or no answer to either of those questions. If the answer is no, This part doesn't matter because if this isn't true, you have zero solutions. It's an inconsistent system. The answer to both is yes. You have exactly one solution. And if you're in this column, meaning these two are equal, but the rank of A is less than n, then you'll have an infinite number of solutions. And this tells you how many free variables, n minus the rank of A. So if you already had augmented matrices in row echelon form, you can figure all this out. It's just three numbers you need. There's the rank of just the A part, and then there's the rank of the whole augmented matrix. Here it's both three, and that's how many columns of A, so you get one solution. Here, let's see. Rank is only two, you got an all zero row here, and same thing for the augmented matrix because it's a zero here. So the ranks are equal, but they're less than n. N is 3 here. You only have 2. The rank is only 2. So you get an infinite number of solutions, and 3 minus 2 is 1. One free parameter. This guy, you can look immediately and say, inconsistent, no solution. This guy, its rank is 2. N equals 1, 2, 3, 4, 5. The augmented matrix is the same, but 5 minus 2 is 3, so we have infinite solution, 3 free parameters. Pretty easy to do with this little decision matrix and just looking at the augmented matrix after doing row operations. You've got a homogeneous system. This chart simplifies because this is always going to be true. If P is all zeros, this is always going to be true. So we have a reduced decision matrix. Is the rank equal? Is it full rank? If yes, you're going to get the trivial solution, which means x equals 0. If no, you get infinite solutions with this many free variables, n minus the rank of A. A homogeneous system is always consistent. You'll always get a solution, at least the trivial solution. Or anything beyond that has an infinite number of solutions. So we can characterize systems of equations. How many solutions and how many free variables?